Welcome back to General Mathematics. In our previous lesson, we learned how to identify different types of functions. Today, we'll take the next step and learn how to sketch their graphs from their equations. Let's begin. So, how do we go from an equation to an accurate graph? We already know that a function can be represented by an equation or by a graph. But when we are given only the equation, what should we do first before we start drawing? That's the question we'll answer in this lesson. By the end of the lesson, you should be able to determine key points of linear, absolute value, quadratic, square root, and cube root functions from their equations. You should also be able to plot those points on the coordinate plane and use the characteristic shape of the function to sketch the graph. We'll also use transformations and symmetry when they are helpful. And finally, you'll learn how technology can be used to check the accuracy of your sketch. Let's connect this with what we learned in the previous lesson. We already know that different function families have different graph shapes. A linear function gives us a straight line. An absolute value function gives us a V-shape. A quadratic function gives us a parabola. A square root function gives us a curved branch. And a cube root function gives us an S-shaped curve. Today, we're going to use what we already know about these shapes to help us sketch them. So, should we determine points before we start drawing? Yes. For an accurate hand sketch, we can follow a simple idea. First, identify the function. Then determine useful points. Plot those points. And finally, sketch the characteristic shape. The points we need, however, depend on the type of function. For a linear function, we can use two convenient points. For an absolute value function, we start with the vertex and then use symmetric points. For a quadratic function, we can use the vertex, the axis of symmetry, and useful intercepts or symmetric points. For a square root function, we start with the endpoint and then find convenient points. And for a cube root function, we start with the central point and then find convenient points. Let's turn that into a simple routine we can use for any of these functions. First, identify the function family. Second, identify the parent function and any transformations. Third, determine the important point or points. Fourth, calculate additional useful points when necessary. Fifth, plot the points. Sixth, use the characteristic shape to sketch the graph. And finally, check the graph. So we're not just drawing a curve and hoping that it looks right. We're using information from the equation to guide the sketch. Let's start with a linear function. Consider f of x equals 2x plus 1. Since a line can be determined using 2 points, we can simply choose convenient values of x and calculate the corresponding y values. Let's use x equals negative 1. 2 times negative 1 plus 1 gives us negative 1. So our first point is negative 1, negative 1. Now let x equal 0. 2 times 0 plus 1 gives us 1. So we have 0, 1. And if x equals 1, we get 3. So we have 1, 3. Once we have these points, we can plot them and draw a straight line through them. Now let's look at the graph we get from those 3 points. We plotted negative 1, 0, 1, and 1, 3. Since this is a linear function, the points lie on a straight line. So this is the graph of our linear function, f of x equals 2x plus 1. There is another way we can determine the points we need. Instead of choosing convenient values of x, we can use the intercepts. Let's use the same function. F of x equals 2x plus 1. To find the y-intercept, we set x equal to 0. Substituting 0 gives us y equal to 1. So the y-intercept is 0, 1. Now let's find the x-intercept. We set y equal to 0. So 0 equals 2x plus 1. Subtract 1 from both sides. We get 2x equals negative 1. Therefore, x equals negative 1/2. So the x-intercept is negative 1/2, 0. Remember, 2 points are enough to determine a line. Now let's move to an absolute value function. We want to sketch f of x equals the absolute value of x minus 2 plus 1. What's the first important point we should look for? The vertex. To find it, we set the expression inside the absolute value equal to 0. So x minus 2 equals 0. Therefore, x equals 2. Then y equals 1. So the vertex is 2, 1. Now that we have the vertex, let's find some more points. For x equal to 1, we substitute 1 into the function. The absolute value of 1 minus 2 plus 1 equals 2. So the point is 1, 2. Now let's try x equal to 3. The absolute value of 3 minus 2 plus 1 also equals 2. So the point is 3, 2. Notice that these points are equally distant from the vertex. 1 is 1 unit to the left, and 3 is 1 unit to the right. Therefore, the points are symmetric about the vertex. Now let's use the points we just determined to sketch the graph. We have the vertex at 2, 1. We have 1, 2 on the left and 3, 2 on the right. Let's plot these points. Then we connect them using the characteristic v-shape of an absolute value function. Notice how the two sides are symmetric. Now let's move on to a quadratic function. We want to sketch y equals x squared minus 4x plus 3. Before we calculate anything, let's identify the coefficients. The standard form of a quadratic is y equals ax squared plus bx plus c. Now compare this with our equation. We have 1x squared, negative 4x, and positive 3. Therefore, a equals 1, b equals negative 4, and c equals 3. We don't choose these values. We identify them from the equation by comparing it with the standard form. Now let's find the x-coordinate of the vertex. We use the formula. X equals negative b divided by 2a. Our b is negative 4, and our a is 1. So we substitute those values. Negative 4 divided by 2 times 1 gives us 2. Therefore, the x-coordinate of the vertex is 2. So we now know where the vertex is horizontally. But we still need the y-coordinate to find the complete vertex. Now let's find the y-coordinate of the vertex. We already know that x equals 2. So let's substitute 2 into the original equation. Y equals 2 squared minus 4 times 2 plus 3. 2 squared is 4. 4 minus 8 plus 3 equals negative 1. Therefore, the vertex is 2, negative 1. Now, the vertical line passing through the vertex is the axis of symmetry. Therefore, the axis of symmetry is x equals 2. Now that we have the vertex and the axis of symmetry, we already have a good starting point for sketching the parabola. We can choose convenient x values on both sides of the vertex. For example, since the vertex is at x equals 2, we can choose x equals 1 and x equals 3. These are equally distant from the axis of symmetry, so the corresponding points will be symmetric. We can substitute these values into the equation to find their y values. We can also choose points farther from the vertex, as long as they are equally spaced on both sides. Another option is to use the intercepts. Intercepts can give us useful points, but they are not required if we already have enough convenient symmetric points to sketch the parabola. Let's see how we can find the intercepts for this particular function. Let's start with the y-intercept. To find the y-intercept, we set x equal to 0. Substituting 0 into the equation gives us y equal to 3. So the y-intercept is 0, 3. Now let's find the x-intercepts. We set y equal to 0. So we have x squared minus 4x plus 3 equals 0. We can factor this expression. It becomes x minus 1 times x minus 3 equals 0. Therefore, x equals 1 or x equals 3. So the x-intercepts are 1, 0, and 3, 0. Again, these intercepts are useful points, but remember that they are just one way of determining points for a quadratic graph. Now we have several useful pieces of information for our graph. The vertex is 2, negative 1. The axis of symmetry is x equals 2. The y-intercept is 0, 3. The x-intercepts are 1, 0, and 3, 0. And since a equals 1, which is greater than 0, the parabola opens upward. Let's plot these points and use the axis of symmetry to help us sketch the parabola. Now we can see the completed parabola. Notice that the graph is symmetric about x equals 2. The vertex is the lowest point of the graph. The points on opposite sides of the axis of symmetry form matching pairs. This shows why the axis of symmetry is useful when sketching a quadratic. Now let's move to a square root function. We want to sketch y equals the square root of x minus 2 plus 1. For a square root function, we begin by finding the endpoint. We set the expression inside the square root equal to 0. So x minus 2 equals 0. Therefore, x equals 2. Then y equals 1. So the endpoint is 2, 1. Now let's find some additional points. For a square root function, it's helpful to choose values that make the expression inside the square root perfect squares. When x is 2, the expression is 0, giving us the point 2, 1. When x is 3, the expression is 1, giving us 3, 2. When x is 6, the expression is 4, giving us 6, 3. And when x is 11, the expression is 9, giving us 11, 4. Now we can plot these points and connect them with a smooth curve. Here is the completed graph. It begins at the endpoint 2, 1 and extends to the right. Notice the characteristic curved shape of the square root function. Now let's move to a cube root function. We want to sketch y equals the cube root of x minus 2 plus 1. For a cube root function, we begin by finding the central point. We set the expression inside the cube root equal to 0. So x minus 2 equals 0. Therefore, x equals 2. Then y equals 1. So the central point is 2, 1. Now let's find some additional points. For a cube root function, we choose values that make the expression inside the cube root perfect cubes. When x is 1, the expression is negative 1. The cube root of negative 1 is negative 1. Adding 1 gives 0. So the point is 1, 0. When x is 2, the expression is 0. So the point is 2, 1. When x is 3, the expression is 1. So the point is 3, 2. And when x is 10, the expression is 8. The cube root of 8 is 2, and adding 1 gives 3. So the point is 10, 3. Now we can plot these points and connect them with a smooth S-shaped curve. Here is the completed graph. The central point is 2, 1. Notice the characteristic S-shaped curve of the cube root function. The points we calculated help us determine how the curve passes through the coordinate plane. Let's bring everything together. What key points should we look for with each function? For a linear function, we can use two convenient points or intercepts. For an absolute value function, we use the vertex and symmetric points. For a quadratic function, we use the vertex, the axis of symmetry, and useful intercepts or symmetric points. For a square root function, we use the endpoint and convenient points. And for a cube root function, we use the central point and convenient points. The important idea is that different function families require different useful points. So, what is our general process? We start with the equation. Then we identify the function type. Next, we determine the key points. We calculate their coordinates. Then we plot the points. After that, we apply the characteristic shape. And finally, we check the graph. So we move from the equation to the points, and from the points to the graph. We can also use technology to check our work. For example, consider y equals the quantity x minus 2 squared minus 1. But we don't need to immediately enter the equation into GeoGebra. First, calculate the key points. Then sketch the graph. After that, use GeoGebra to check your work. Without technology, the process is calculate, plot, sketch. With GeoGebra, the process is enter, graph, check. Now let's see what this looks like using GeoGebra. We enter the equation into the graphing calculator. GeoGebra displays the graph for us. We can compare it with our hand-drawn graph. Remember, technology is helping us check our work. It does not replace the mathematical process of determining the important points. Before we consider our graph complete, let's check a few things. Are the calculated points plotted correctly? Are the intercepts correct when they exist? Is the vertex, endpoint, or central point correct? Does the graph have the correct characteristic shape? Does the graph extend in the correct direction? And finally, does the graph agree with the equation? These checks can help us catch mistakes before we finalize our graph. Let's summarize the main ideas from today's lesson. A function's equation tells us which important points to determine. Different function families require different key points. Linear graphs may use convenient points or intercepts. Absolute value graphs begin with the vertex. Quadratic graphs rely on the vertex and symmetry, and we can use convenient symmetric points or intercepts. Square root graphs begin at an endpoint. Cube root graphs are organized around a central point. And technology such as GeoGebra can help us verify a sketch. That gives us the main strategy for moving from an equation to an accurate graph. Now, let's reflect on what we learned. An equation can tell us exactly how values are related, but a graph allows us to see that relationship. It can help us notice patterns, trends, and changes that may not be immediately obvious from numbers or equations alone. So, graphs are not just something we draw in mathematics. They help us make sense of the world around us. And that brings us to the end of our lesson. Thank you.